In this video, we're going to look at linear correlation, just some basic information about it, how to calculate it by hand, and how to calculate it using StatCrunch. So when we say the phrase linear correlation, what we're looking at is there a straight line relationship between variables. And if we look at the term linear, the root word of linear is line. So we always want to make sure when we're doing linear correlation, we are only looking at straight line relationship between the two variables. Now, correlation allows us to determine if there is evidence to state that there is a linear relationship. And then it's also going to give us an idea of how strong that relationship is. Now, one thing to keep in mind is that correlation does not imply cause and effect. So this is an issue that we sometimes run into, especially when we look at media. If it's found in a study that there's a correlation between two items, oftentimes it'll be assumed that one causes the other, and that is not what correlation does for us. Now we're going to look at the 4 different types of correlations that we're going to be working with, and then just kind of a generic overview of what their strengths could look like. So if we hear the term positive correlation, what that would mean is that if we had a scatter plot like this one shown here, and if we were to put in a line that approximate those values, we would consider this one to be positive because the slope of my line would be a positive slope. It's increasing as it goes to the right. Now this one right here would also be positive because my values are increasing as they go to the right. But since these dots over here are a lot closer together, a lot closer to being a straight line, this would be a stronger correlation than what our original values were over here. So in our original ones, our data points were scattered out a little bit more, and on this one, they are much more closely related to a straight line. So the closer the dots are to a straight line, the stronger that your correlation is going to be. Okay, now for our next category, if we look at negative correlation, that indicates when I draw my line in here, if I look at the slope of my line, it would be a negative slope because my line is decreasing as I move to the right. So this type of a trend would be considered to have negative correlation. And again, if we look at the different strengths between them, the second example that I have here would be stronger negative because as we look at the dots, they are a lot closer to the straight line than what our original ones were. Now we can also have the category of nonlinear. Now nonlinear indicates that we have a pattern, but it's not a line. So if I look at the example we have here, there's definitely a pattern going on here, but we can see that it's not a straight line pattern. So when we see a pattern, but it's just not a straight line, we would consider that to be nonlinear correlation. And then our last category that we're going to look at is no correlation. So now when I look at this scatter plot, we can see that there's values kind of all over the place. There doesn't really seem to be any place to put a nice straight line, either positive or negative. I can't really see a nonlinear pattern like we had in our last one. So when we have a scatter plot that looks like this, we would say there is no correlation. So there doesn't appear to be any relationship between these particular two variables. Now we're actually going to need to calculate the correlation coefficient, and that's going to be the value of the correlation. It'll always be between -1 and 1, and this is going to allow us to determine mathematically whether or not we have correlation. Now there's going to be 2 different symbols that we use for correlation. If we use the lowercase r, that's an indication that our correlation is just from a sample. And if we use the Greek letter rho, that's an indication that our correlation is actually from a population. This is going to tell us the strength of the linear relationship. And again, it's always going to be between -1 and 1. Now, as far as these 2 topics go, a correlation of +1 would mean that every single point in my data set was perfectly on a straight line. And a correlation of -1 would indicate that every single point in my data set was also on a straight line. But again, the difference would be that the positive correlation is increasing as we go to the right, and the negative correlation is decreasing as we go to the right. Sometimes you might hear this called a direct relationship, where one increases, the other increases. And for a negative, it might also be called an inverse relationship, as one variable increases, the other one decreases. Those are all terms that are giving us the same type of a picture for these different scatter plots. Now, what we're going to look at now is the formula that goes along to calculate linear correlation. There are some things that we need to do first. The first thing that you always want to do is you always want to make a scatter plot of your data. That way we can look at it and we can see, does it seem to be positive? Does it seem to be negative? Or is there a nonlinear relationship that we're working with? The biggest issue that people run into is if you skip the scatter plot, it's very easy to miss the nonlinear patterns. So you always want to start with a scatter plot to get a visual inspection. And then the other thing you want to do is from your scatter plot, you want to look to see if there's any outliers. So an outlier is a value that doesn't really fit the pattern of the rest of them. So let's say our scatter plot looks like this, and then we have a point that's clear over here. Well, it looks like this group of points right here kind of fit a nice positive trend line. But this point is way out there. It doesn't seem to fit the pattern. So we would definitely want to investigate that particular point, because outliers can have huge effects on our value of our correlation. They are very influential points, so we have to determine what we're going to do with them. Now, with an outlier, if we know that the outlier was an error, then it needs to be eliminated before we calculate the correlation. But if we're not sure about that, whether it's an error or not, then we need to calculate the correlation with the outlier included in the group, and we need to calculate the correlation without the outlier in the group, and then we would compare those values. Okay, so here is our formula to compute the linear correlation by hand. Now, it looks a little bit overwhelming. We can see that we have a lot of different X and Y's in here, and we have several different sigmas in here. But what we are going to do is we're going to break it down and we're going to calculate it with the help of a table. But once we get this calculation done and we have the value of our R, so we have the value of our correlation, what we would do is we would compare the absolute value of R to the critical value from a standardized table. And then if our absolute value of R is greater than or equal to that critical value, then there is enough evidence to say that we do have a linear correlation. All right, so what we're going to do is we're going to start with an example here. And I have just a very generic example. It says, let X represent the number of children in a household, and let Y represent the amount spent on groceries per household per week, measured in dollars. So here I only have 4 data points because I want this to go a little bit quicker. And what we're going to do is we are going to go through the process to find our correlation. Now, if you remember, the first thing we need to do is we need to create a scatter plot of our correlation. I would recommend doing the scatter plot using technology. Alright, so I have StatCrunch opened up here, and as you can see I already have my data values entered. I have my X values in the variable 1 column and my Y values in the variable 2 column. So now in order to see a scatter plot of this, so we can check if there's the possibility of a nonlinear relationship, I'm going to go to the graph menu, and then I'm going to scroll down to scatter plot. And it's going to ask me to select my X variable and to select my Y variable. And then when I press compute, it will generate scatter plot for me. So as I look at this, what I'm really looking for is whether or not there is a pattern to my points that are not a straight line. And as I look at them, I don't see any distinct curve or repeating pattern or anything like that that would indicate that it might be quadratic or logarithmic or sinusoidal or anything like that. So it looks like we probably have a straight line pattern here. So now that we've seen that our scatter plot doesn't show any nonlinear pattern, we're going to go ahead and use this table to generate some of the values that we're going to eventually need for our formula. So my first column here says I need to take x times y, and the reason I'm doing x times y is because, as you can see over here, that's one of the components of my formula that I'm going to need, is all these x times y's. And same thing with my x squared column and my y squared column. Those show up in my formula. So I'm going to do these computations off to the side first, and then we'll transfer them into our formula. So my first value here, x times y, I would take 2 times 200, and that's going to give me 400. I'm going to do 1 times 175, and that's going to give me 175. 3 times 210 is 630, and 0 times 150 is 0. So you'll always want to make sure that you keep the pairs together. So I would not want to do like the 2 times 175 because they weren't a pair. You always keep the pairs together. Okay, my next column is x squared column. So I'm going to take each of my x values and I'm just going to square them. So I would have 4, 1, 9, and 0. And then my last column here says I need my y squared values. So I'm going to take all my y values and I'm going to square them and put those in here. So 200 squared is 40,000. 175 squared is 30,625. 210 squared is 44,100. And 150 squared is 22,500. Now what I'm going to do is I'm going to come over and I'm going to start looking at my formula. Now in my formula, n stands for the number of pairs that I have. Well, I was originally starting with four pairs of values. So I'm going to start with r equals, okay, and my n is 4. Now this next component here, I have the Greek letter sigma, which tells me I need to have the sum of my xy values. So I need to come over here to my xy column, and in the bottom, I'm going to put my sums, because that's what this Greek letter over here is telling me to do. I need to find the sums. So when I add my xy columns all together, I am going to end up with 1,205. So that's going to be the value that I put in for that whole item there. Okay, now my next item here, I see another sigma in there, which means I need the sum of my x values. So I need to come over here into my chart and I need to add up all my x values here. So 2, 1, and 3 gives me a total of 6. So that's going to go where the sum of x is. And then the last item I need for the numerator here is the sum of my y values. So I need to add up all my y values there, and that's going to give me 735. Now in my denominator, I have the square root, and again I have an n show up, so I have a 4. And now this next piece here says I need the sum of my x squared values. Well, I have all my x squareds here, so I just need to go ahead and add all those up, and that gives me a 14, and that's what I will put in place there. And then now this one says I need the sum of my x's squared. So the sum of my x's was 6, and then I have to put a squared on that. And then I have another component here. I have the square root. Again, my n shows up, so I have a 4. And I need the sum of my y squareds. So I would come over to my y squareds column, and I need to add up this entire thing, which turns out to be 137,225. And then the last component I have here is the sum of my y's, that quantity squared. So the sum of my y's was this 735 over here, and I have to have that squared.